Hey everyone, welcome to Chemistry 40 with Dr. Carroll. I hope you're all excited for this first lecture in Unit 3, all about rates of chemical reactions, how fast reactions go, known as chemical kinetics. And so you all have your booklet. This unit, there's lots of words, lots of descriptions, not that much math, a little bit, not that much, but lots of terminology. So remember, Unit 1, we started really small, looking at electrons, building them up into atoms. Unit 2, we took those atoms together, formed molecules, crystals. Now we're going to see how fast it takes to form things, how fast it takes to break things apart. That is what chemical kinetics is all about. So I'm just going to read through. The blanks are filled in for you, so you can just highlight them. Chemistry focuses largely on chemical reactions. Some reactions, such as rusting, occur very slowly, unless it's my old Chevy Cavalier, while others, like explosions, occur quite fast. Kinetics studies the rates of chemical reactions. Some reactions do not occur in a simple step, some occur in several more complex steps. So part of kinetics is studying the reaction mechanism of a chemical reaction, the detailed series of steps. So reaction mechanism is a detailed series of steps. Some reactions, just one step. That's called a simple step. If the reaction is more than one step, it's called complex. It's important for chemists to understand the mechanism of a reaction and the factors that affect its rate. With this knowledge, chemists can control chemical reactions in order to make them happen or not, and to control the rate at which they happen. So chemists want to be in control. We are control freaks. We want a reaction to happen. If we're making product to sell out market, we want to make as much as we can, as quickly as can, with the greatest profit margin. That is the capitalist dream, is it not? Sounds like Shark Tank, doesn't it? So we look at some things in general and then we pinpoint them. That is the strategy for the first part of this chapter. So what factors affect the reaction rate? How can you make something go faster? One is the nature of the reactants. What are the reactants made of, and how many bonds are there? We know that in a chemical reaction, we have to break bonds and we make new products. The breaking of bonds requires energy, and the forming of bonds releases energy. Otherwise, you wouldn't form bonds because you wouldn't become more stable. You want to become more stable energetically. There's another thing called entropy we'll get into in the next chapter. To break the bonds, you got to put energy in. So it makes sense that the strength and number of bonds will affect the reaction. So the weaker and less bonds to be broken, I'm over here, the weaker and less bonds to be broken, the faster the reaction. Reactants that require the breaking of covalent bonds will be slower than those involving ionic bonds. That's usually the case, not always. Ionic compounds are already separated into ions, so these are faster acting. That's true. If you already got an aqueous solution, if already separated into ions, then your reactions will be more quickly. By the way, when we talk about the rate of reaction, if you have a faster rate, then it takes less time. If Mr. Shahinfar and I are running down the hallways and he's faster than me, then his speed will be greater than mine. So it'll take him less time to run the halls than it will me. And I think that's true. We'll have to try it one day. Here we have reactions. Which will be the fastest between reaction 1 and reaction 2? Reaction 1, we have hydrogen plus iodine going to 2HI gas. So we are breaking hydrogen bond and iodine bond, then forming HI, right? Think of it like this. Here's hydrogen. Here's iodine. We break this, and then we form an HI and form another HI. Okay, it's all in the gas phase. That's nice. That makes it faster. But in the second one, you look at it first, you say, oh, there's all this extra stuff, it's going to be slower. Well, at the same temperature, same concentrations, in fact, this is faster. Because if I break this down, what I really have, all in the aqueous phase on the left-hand side, lead ion, nitrate, Na+, we'll have another Na+, I-, I-, that's all on the left-hand side. The right-hand side's a solid, so that doesn't break up. That's a precipitate coming out. And then I got an Na+, an Na+, an NO3- and an NO3-. Those are just spectator ions, the Na+s and the NO3-. You might remember that from grade 11. And so really all that's happening is the lead is connecting up with the two iodides to form a solid. So you aren't breaking any bonds, you're just forming bonds, so that's actually faster. So the second reaction is faster. Again, we're assuming the same temperature. When comparing reactions with similar bonds, the greater the number that have to be broken, the slower the reaction. Think about dismantling an object. If you want to fix it, the more parts that you need to separate, generally the longer it will take. I like to think of it as Legos. Let's say your little sister took your Legos and built this big dollhouse or something with it. Then you wanted to build a Star Wars fighter pilot thingy. You'd first have to break apart all her dollhouse and then to build it. But if you were just starting from fresh, it'll be faster. Here we have two reactions, both in the gas phase, both involving covalent molecules. 2NO plus O2 goes to 2NO2, and 2C8H18 plus 25O2 goes to 16CO2 plus 18H2O. All in the gas phase. The second one is going to be slower because there's more bonds that have to be broken and reformed. First reaction is therefore faster. The rate is higher. It only involves the breaking of one oxygen-oxygen bond and two NO bonds. That O bond is actually a double bond, but that's okay. It is a bond, 4 electrons, still a bond. Yeah. If the reactions have similar bonds and similar number of bonds, okay, so covalent bonds, let's say, same numbers, then it's the phases that are going to be dominate. Aqueous and gases are faster than liquids and then solids. Solids are the slowest because you have to overcome these forces of attraction between the particles in the solid. Okay. So here I have which equation of the following pairs would occur the fastest? So here it would be, well, look at it. It's going to be the first one. Second one is solids, so you'd have to break interatomic forces. So this would be faster because the first one is just aqueous coming together. The second one, again, the first one's faster. Look, again, somebody say, oh, it looks like there's more stuff. Yeah, there's more stuff, but you aren't breaking any bonds. They're already in ions swimming around. In the second case, you are breaking bonds. Second one, which of these would occur faster at room temperature? Again, it would be the first one because they're already swimming around in solution, so you don't have to break bonds. The second one, you got to break the chlorine bond there. Next one, which would you predict to be fastest? Well, the fastest one here would be this one because you're not breaking any bonds. You aren't even forming any bonds. All you're doing is transferring electrons around. This is something that we're going to learn way near the end of the course in more detail. It's an oxidation reduction process, also called a redox process. Okay? So let's look to temperature changes. That's another way to, another factor. And really, the hotter something is, the greater will be its speed, the greater will be its kinetic energy. Some molecules will now have, hopefully, enough energy to form products. In other words, they'll have the activation energy worth of energy. So collision theory is something we're going to hear about this chapter. There's some good videos in our website about the chapter. Collision theory means you have to have things hit each other if you're going to form product. If you want to form a fender bender, let's say you're trying to rip off MPI for some weird reason, you have to have someone hit your fender. If they don't hit your fender, you aren't going to get a fender bender. According to collision theory, the rate of reaction is determined by the frequency or the number of successful or effective collisions. I like to use the word effective collisions. The more effective collisions, the greater the rate of reaction. An effective collision is a collision between reactant particles with enough energy and the correct orientation. So you have to hit properly. You have to hit the fender if you want a fender bender, not the glove compartment, right, from the side. So at any given temperature, some particles are faster, some particles are slower, some particles are more energetic, some are less. there's a fixed number of particles that produce an effective collision. It might be really small, it might be really large, but they have the activation energy, E activation energy, which is also called E sub A. Typically, as temperature increases by 10 degrees Celsius, the rate of the reaction doubles. That's not always the case, but it's a rule of thumb that works sometimes. So, more than 50%? Sure, why not? As the temperature increases, the rate of the reaction doubles. So here's a kinetic energy distribution curve. So we've got the number of particles with a certain kinetic energy versus the kinetic energy. And here's my 0, and kinetic energy is increasing. And you see this region here, if you integrate under this part of the curve, those particles will have enough activation energy, and if they're hitting with the proper orientation, they will form effective collisions. An effective collision is going to create a product. If they don't have enough energy, if you're trying to do a fender bender and you just touch the back bumper of the other car without making any dent, then you don't have enough energy and you will not form an effective collision. It will not be an effective collision. Okay. I like to think of this almost like it's has like a kinetic energy. Remember from physics, it's 1/2 mv squared. But I like to think of it on the highway. Let's say the speed limit is 100 kilometers per hour, so most people are clustered around the 100 kilometers per hour. Then there's some speed merchants going 180, let's say, and they're the ones who are going to get in collisions. And then there's some slowpokes, the old men with hats like me, who are going at 3 kilometers per hour, and we aren't going to form many accidents. Actually, we do, don't we? Okay. Every reaction has its own specific kinetic activation energy, also known as threshold energy. So if my activation energy was smaller, if it was over here for a reaction, well then at a given temperature I'd have much more particles forming effective collision. That's what I just said here. The lower the activation energy is, the more particles in the system will possess enough energy to produce a reaction. Here, at a given, let's say my activation energy is over here. Okay, I'm just putting it in here. It doesn't change much with temperature, the activation energy. But you see at a lower temperature, O2 is 25 degrees Celsius, you see a cluster here and just a few molecules to the right of the activation energy. But if you go to a higher temperature, yeah, you're going to have more collisions, but more importantly, you're going to have more effective collisions because you're going to have more particles which have at least the activation energy. All of these, excuse me, have the possibility of forming effective collisions if they have the right orientation. And here we're even fancier. We have 3 temperatures, so I could say, okay, which one is the higher temperature of the 3? So T3 is higher because it's skewed farther to the right than T2 or T1 slanted to the right. And so T3 is going to have more effective collisions than T2 than T1. So which temperature do the most particles possess more than the activation energy and are able to make successful collisions? That would be T3. Okay, so you can read that. Lowering the temperature, we said all this. Okay, so here we have an example question. Based on the following, which reaction will have a faster rate? Well, A is going to be faster because the, no it's not, B is going to be faster because the activation energy is smaller, so B is faster. Okay. Also, which reaction would benefit most in terms of increased rate if the temperature were increased? Well, I'm so far to the left with B that if I increase the temperature of A, well, that's going to benefit more. If I increase the temperature of B, well, it'll flatten out. It's not going to help much. So B is faster because the activation energy is less. Okay. Another factor that affects the rate of a chemical reaction, how fast a reaction happens, is changing the concentration. Concentration refers to the amount of reactant per unit volume. The units are moles per liter, molarity, right? Remember that from grade 11? Molarity, which equals moles divided by liter. It can be used for aqueous. It can also be used in gas phase, because gases occupy whatever volume they're in. So if I have more reactants, I'll have more particles in a given container. More particles, some of which will have the activation energy worth of energy, and you'll get more collisions. So here we have bang, 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 but if I double to 4, I get all sorts more collisions going on. So the greater the concentration, the more particles you can produce. It's like an assembly line. If you got more parts in a given strip of conveyor belt, you can produce more product in a given amount of time. Okay. We can think of this in terms of collisions with cars. During rush hour, there are more accidents because there are more vehicles on the road at one time. The frequency of collisions increases because the concentration of vehicles is larger and the space between each vehicle is less, increasing chances of collision. Okay, so we've got more cars in a given amount of time. That means in a given amount of volume, so the concentration goes up. So you're going to get more collisions. Here's a question here about concentration. Let's say we have hydrochloric acid and zinc, so HCl and zinc. Will this reaction occur fastest using 6 molar, that's really concentrated, hydrogen chloride, or half molar? Well, the answer is going to be 6 molar. That's more concentrated. You're going to get more collisions. Of those collisions, some of them will be effective, more so than if you just had half molar HCl. So in our 6 molar solution, we're going to have a greater rate of reaction. It's going to take less time if it's more concentrated. Okay, so we surveyed through it, and we're going to return to concentrations later on in this chapter. Then we talk about catalysts. They're a way to speed up a reaction. A catalyst is a substance that speeds up or initiates a reaction without itself being permanently changed or used up. It may be used up in a step in the reaction mechanism, but it does regenerate itself. So catalysts speed up the rate of reaction. Here's something called a potential energy profile, and we're going to look at that in more detail as we go through the course, through this chapter. So potential energy, I don't know, let's say units of kilojoules. You have some value, let's say 0 for the reactants, and then you have a value below 0 for the products. I don't know, let's say -20, just making up a number there, that's okay. So this is an exothermic profile that I'm drawing here. If the products are lower energy than the reactants, it's exothermic. Remember, H is heat content, or enthalpy is another name for that. And so we just have a curve here. The particles are coming together. They form an unstable condition, a creature called the activated complex at the top of the hill there. So this double cross is a symbol that people use for what's called the activated complex. So the activated complex isn't a number, it is a collection of interacting particles. Kids always think it's a number. It's not. It's a collection of particles that come together and then have to decide whether they're going to tumble back down to the reactant side or tumble further on to the product side. And from wherever the reactants are to the top of the hill, that is called my forward activation energy. Okay, so if I'm going from reactants through the activated complex to products from left to right, that is the forward activation energy. And from the products, and we're going to learn that the products keep smashing into each other, and they're going to go back to reactant side. If we just start with reactants to begin with, they'll hit each other, form some effective collisions, go to the product side. But as time goes by, the product molecules are going to hit each other and go back to the reactant side. So from the product to the top of the hill, that is called the reverse activation energy, EA reverse. Now, you see what I've done here is I've lowered the activation energy by putting in a chemical called a catalyst. So that is the forward activation energy, but catalyzed. So what can I stick that in there? EA forward catalyzed. And from the product to that point would be EA reverse catalyzed. So a catalyst will find an alternate reaction pathway, create an alternate reaction pathway to get to the products, and it will lower the activation energy. Okay, that's what we say there on page 6. So catalysts provide an easier, lower path for the reaction to proceed. Lowering the activation energy of a reaction increases the number of particles with enough energy to produce an effective collision. More particles with activation energy means more frequent effective collision and an increased reaction rate. If I go back to this picture, you can almost think of it, let's go on a bike trip from R to P, okay? And so we've got a high hill here if we didn't have a catalyst. So some of us will negotiate that hill well and get to the product side, but some will go up, come back down. Some like me will just go up to here and down. If you find a secret shortcut, well, some people will still want to challenge themselves and go up the highest part of the hill, but more people will take this shortcut to get to the product side. So the rate of getting to your destination increases if you use a catalyst. And catalysts are reformed. Catalysts can be expensive, but they can be used lots of times before they finally deteriorate. They aren't perfect. So in industry, sometimes you pay lots of money for a catalyst, but it's used a lot. Here's a nice picture where we have both a potential energy profile on the left here and a distribution of kinetic energy on the right. So you see where you have the activation energy for the catalyzed and the uncatalyzed case. So that's just putting both pictures together. Another way to increase the rate of reaction, if we're dealing with gases, it's not really pertinent for other phases of matter, but if you change the pressure, that usually only affects the reaction rates of gas, so increasing the pressure will increase the rate. Pressure is the force of particles upon the walls of the container, given symbol P. The number of particles increases without changing the volume, the pressure increases. Okay, that is Avogadro's law, is it not? There are 3 ways to change pressure. We can add more products to a fixed container, right? We can increase or decrease the volume. That's Boyle's law, right? Pressure goes up, volume goes down, pressure goes down, volume goes up. That's Boyle's law. So we can play around with that to change the pressure, and in so doing, possibly change the rate of the reaction. Or we can add a inert gas. Inert is another name for unreactive. So there are ways to change the pressure, and those are 3 of them. If we add more reactant particles, the concentration increases, causing an increased rate. If the pressure is reduced by removing reactants, the rate decreases due to a decreased concentration. If you decrease the volume of a container without changing the number of particles in the container, the concentration of the reactants increases. Spaces between the particles decreases, increasing the chances of collision. If the concentration increases, the reaction rate increases, and the time for reaction to happen decreases. So that's dealing with gases and pressure, and there's Boyle's law, where we squeeze everything in like that. Another way to increase the rate of reaction is by breaking things down into smaller bits, especially solids. So increasing the surface area of the reactants by crushing, grinding, or other means increases the number of particles of reactants in contact. The rate of reaction increases when the surface area increases, like a sugar cube in coffee compared to a spoonful of sugar, which helps the medicine go down. So here you have a sugar cube, so you dissolve it in water, you just have collisions in the outer faces of the cube first before you get to the inner part. If we make it into a powder first by grinding it, perhaps using a mortar and pestle, my dad was a pharmacist, so we had all sorts of these all around. Maybe some of you have these as like garlic presses or spice bowls or something like that, or the Spice Girls, I don't know. And you have water attacking a powder, well, you're going to more easily dissolve the sugar cube. So if I increase the surface area, the frequency of effective collisions increases and the reaction rate increases. Kindling for trees, when you start a fire, you start with small pieces first. You don't just take a lighter and put it on the end of a huge log. That's not going to work so well. What did I write Baba tea here? A Baba, a grandma. Maybe some of you have a great-great-grandma who drank their tea like that. They poured their tea into a saucer, and that helps to cool things off. And then they put a sugar cube in their teeth, okay? And then they slurped up the tea so it filtered through the sugar cube. Now some people say, oh, that's not good for your teeth, but my Baba came from a place where you didn't really have much sugar, and she was rushed out of her village and didn't really get a chance to savor much of anything. So when she came to Canada and worked hard, was able to get some sugar cubes, she still savored them. She didn't want that taste of the sugar with the tea to disappear really quick. She wanted to slowly enjoy the sweetness in the tea. So, email me if you've got a relative who drinks their tea like that. There you go. So what have we learned in this lesson so far? The number and strength of the bonds affects the rate. Increasing the temperature increases the rate. Increasing the concentration of reactants increases the rate. Pressure increases the rate. Using catalyst increases the rate. There's both homogeneous and heterogeneous catalysts. We'll get to that later in the chapter. Increasing the surface area by chopping things into smaller bits also increases the rate. So those are all ways to increase the rate of a reaction. Then these practice questions are just repeating everything we had. So let's keep going a little bit and talk about rates. I mean, we've been discussing them. Let's discuss them a bit more here. So we'll bundle this into our first lecture here. It'll be a longer one, but that's okay. Hopefully your rate of comprehension is a high one. When we hear the word rate, we think of speed of velocity in terms of rate of motion. We're not going to read everything here. What's rate? Chemical reactions when a new substance is formed. You have reactants on the left, products on the right. You have a chemical reaction. The rate of reaction refers to the speed with which a chemical reaction takes place. Okay, we can measure rate by seeing how long it takes for it to come to completion, not conclusion. Slow reactions take a longer period of time. Explosion is very fast because the explosive all burns up in fractions of a second, while burning a wax in a candle could take hours. But it's still all relative, so you want to find a more mathematical way to talk about rate. We can talk about rate displacement over time in physics. We can talk about interest rates, talk about the rate of pay at Cineplex Odeon, all this sort of stuff. But we're going to talk about rate as the measured change in some chemical or physical property over the time for the change to occur. And really we're going to relate that eventually to the change in the concentration of a reactant or product over the change in time. So the rate is the change of a reactant or product over the change in time. So the rate of reaction is going to be units of molarity per second, moles per liter per second, right? M divided by S. This is the same thing as writing ms to the minus 1. And get used to writing units with these negative exponents. They're more helpful. So here we have A plus B goes to C plus D. It's exothermic. Heat is given off. B has a green color. D has a red color. Rate can be measured in terms of different ways. We could measure the temperature change over time, right? As the reaction proceeds, the system will increase in temperature. The faster heat is produced, the higher the rate. So you could look at how quickly the temperature goes up. And then relate that to concentration and get the rate that way. Pressure, you could use a manometer and see we're forming a gas, which is capital letter C is the chemical, which is the gas in this example. How much of that is formed per second? That's a way to measure the rate. We could look at mass changes. We could measure the mass increase of the gas or mass decrease of the reactants. We could look at color changes. We could get what was D, that was red, right? So the deeper the red is and the quicker it comes, you could relate that using a spectrophotometer, which is some fancy machine to measure absorbances of wavelength, transmittance, you could relate that and get the rate that way. Look at pH changes, conductivity changes, things like that. But we're going to put it all together, and here's my better way to write it. Rate is the change in concentration over change in time. We can look at instantaneous rates, just like in physics, or average. And we're going to focus more on average rates. Okay, so the average rate is expressed as the change in concentration of A over time, or the change in concentration of B over time. I'm using absolute values here. You don't want to quote a rate as a negative value. That's just a convention that chemists have agreed upon. So we're just going to write rate as the change in concentration over the change in time with those absolute value bars. And change is final minus initial. So if we're looking at concentration A, the average rate is in absolute value bars A final minus A initial over T final minus T initial. Okay. So let's look here. An example, we got CO gas plus NO gas goes to CN gas plus O2 gas. The rate can be written in any of these ways. Now here I used an old-fashioned way of doing it where I did put a negative sign in front of the reactants because they are disappearing as time goes by. So the change is negative. So if I put a negative sign in front of the delta symbol, then it becomes a positive sign. So here's an example. Suppose it took 50 seconds to go from 2 molar to 0.5 molar. Calculate the rate in moles per liter per second. So I end up with 0.5. I started with 2. Happened in 50 seconds. So on average, the rate of this reaction is 0.03 moles per liter per second. Suppose instead I had a set of data where it took 2 minutes for oxygen to go from 0.7 to 0.9 molar. So the rate goes up. Sorry, the rate doesn't go up. The concentration of oxygen goes up from 0.7 to 0.9. And that took, I wanted it in moles per liter per second. I'll be specific about that. So I have to convert to minutes to seconds. 60 minutes times 2. 60 seconds per minute times 2 minutes is 120 seconds, and you get 0.0017 moles per liter per second. In the third one, it takes 5 hours for CN to increase by 0.3. Calculate the rate. So here I don't give you the initial amount of CN or the final. I just tell you it increases by 0.3. So that is going in the numerator. It's an increase. I don't need any negative sign to make it positive. It already is. And 5 hours, an hour is 3,600 seconds. So I get 1.7 by 10 to the minus 5 moles per liter per second. So that's just a quick example of talking about rates. Okay, we'll get into collision theory in more detail in our next lecture, but I think that's good enough for now. So reread those and become experts, and look at some of those videos that we've curated on our cool website. Have fun.